Hello, welcome back to our series of current electricity. This is lesson 4A level physics prepared by Joseph Mayanja. In the previous lesson, we introduced Ohm's law, that relationship that relates the current and the PD discovered by Simon Ohm. And we said that Ohm's law states that the current flowing across the ends of the conductor is directly proportional to the potential difference across its ends, provided temperature and other physical factors are kept constant. In today's lesson, we are going to discuss resistance. As electrons flow from one end to another across the ends of the conductor, they encounter some opposition to their flow, and this opposition is what we call the resistance. So by definition, we are saying resistance is the opposition of a conductor to flow of current, and it is measured in ohms, and the symbol is this one down here. The resistance of a conductor is just the ratio of the potential difference across its ends to the current flowing through it. Resistance becomes the ratio of the potential difference V across its ends to the current flowing through it, I. A good conductor usually has low resistance. It has low opposition to flow of current. That is why we call it a good conductor. And good insulators usually have high resistance to flow of current, and we have several of these ones. From Ohm's law, we are saying the resistance of the conductor is the ratio of the PD across its ends to the current flowing through it. We know that Ohm's law suggests that V is equal to IR. Then when you divide through by I, you come up with the relationship. Resistance is just the ratio of V to I. So we've said that resistance is measured in ohms, and this one takes us to the definition of an ohm. Since an ohm is SI unit of resistance, so we are defining it as the resistance of a conductor if a current of 1 ohm flows through the ends of the conductor when the PD across it is 1 volt. So when you have a current of 1 ampere flowing across the ends of the conductor and the PD across it is 1 volt, then the resistance or the opposition to flow of that current offered is what we are calling an ohm, and it is measured, and 1 ohm is simply equal to 1 volt per ampere, because resistance from the relationship is given by V divided by I. Remember, V, which is the voltage, is measured in volts, and the current, which is the I, which is the current, is measured in amperes. So this one gives us the relationship which we are calling volt per ampere. Therefore 1 ohm is equivalent to 1 volt per ampere. Resistors in a circuit can be arranged in 2 major ways, depending on what whoever is arranging the resistors want. Resistors can either be arranged in series or in parallel, and in several cases you've seen resistors arranged in a circuit either in series or in parallel, and we are going to discover what happens if resistors are arranged in series and what happens if resistors are arranged in parallel. Let us look at resistors in series. Let's consider this circuit, and in this circuit we have resistor R1, resistor R2 and resistor R3, and a cell of PDV producing a current I. Then we have PDV1 across resistor R1, PDV2 across resistor R2, and PDV3 across resistor R3. When resistors are arranged in series, the current flowing through them is the same. Like you can see here, the current produced by a cell of PDV, which is I, is the same as the current that flows through R1. It is the same current that flows through out of R1. It is the same current that flows through into R2. It is the same current I that flows out of R2, and then it's the same current I that flows into R3, and it is the same current that flows out of R3. Now the total PD V, which is this PD, will be equal to the sum of V1, V2 plus V3. Let us call this one equation 1. Now from Ohm's law, we know that Ohm's law suggests that V is equal to IR. Then we shall have V1 being equal to the product of the current times the resistance. Then V2 is the product of the current I that flows through R2 times its resistance R2. Then V3 is the product of current, which is I, times the resistance R3. Now, when we substitute in that equation 1, we come up with equation 2 here. Wherever we see V1, we bring this expression. V2, we bring this expression. V3, we bring this expression. Therefore, we come up with V being equal to I R1 plus I R2 plus I R3. You can see that I is the same because we said that when resistors are arranged in series, the current usually flowing through them is the same. Now, from this relationship of Ohm's law, we can see that our V is also IR. So we substitute for V and then we come up with that expression. Now, from equation 2, we can now factorize out I. So we come up with this bracket. Let us call this one equation star. When you divide through by I on both sides, that I goes with that I and that I goes with that I, then you come up with this expression R being equal to R1 plus R2 plus R3, where R is the total resistance. Let us look at this example. In this example, we want to find the total resistance in this circuit. Like you can see in this circuit, we have 3 resistors, the 2 ohm resistor, the 4 ohm resistor, and the 3 ohm resistor, and the 1.5 volt cell. Since they are arranged in series, the current flowing through them is the same, and it is I. But we know that when the resistors are arranged in series, if we want to get the total resistance can be calculated from the expression we derived, which is you just get the sum of the individual resistances. Therefore, the first resistor is 2 ohm, the second resistor is 4 ohm, and the third resistor is 3 ohm. And then that one gives you 9 ohms. And that is the total resistance. If you have 2 resistors arranged in series, then you are just going to add the individual resistances. If there are 7, then you will have to add the individual resistances. And that is how you get the total resistance when the resistors are arranged in series. Now let us talk about resistors in parallel. In this circuit we have a cell of PDV connected across 3 resistors, that is R1, and the current flowing through R1 is I1. Then we have resistor R2 and the current flowing through R2 is I2, and we also have resistor R3 and the current flowing through that resistor is I3. We can see that at this junction current splits. The current which was I, when it reaches this junction, it splits, and we are calling that junction A. We have 2 junctions, junction A and junction B. We have to emphasize that these 3 resistors, the PD across them is the same, which is V. The PD drop across all these resistors is V, and it is the same. When resistors are in parallel, the PD across the ends is the same. Like we can see here, at this junction A, the current splits into I1, then I2, then I3. But we are saying, since these resistors are in parallel, the PD across is the same. The PD across R3 is V, the PD across R2 is V, and also the PD across R1 is V. Now the total current at this junction, using the junction law or the first Kirchhoff's law, current I will be equal to the individual current I1 plus I2 plus I3. From Ohm's law, V is equal to IR. This takes us to I being equal to V divided by R. That implies that for I1, it will be V divided by R1, and for I2, it will be V divided by R2, and for I3 it will be V divided by R3. We can see that V is the same. Now from this equation 1, we can now do the substitution, and we say that wherever we see I1 in this equation, we substitute with the equivalence of I1, which is V divided by R2. It is the same thing for I2, it is the same thing for I3, and then we come up with this equation. Let us call it equation 2. Now from Ohm's law, we can see that also I is equal to V divided by R, where this capital R is the total resistance. So from here, we can now factorize out V from this term, and from this term, and from this term. Then we factorize out V. Then when we divide through by V, you come up with R, 1 over R equaling to 1 over R1 plus 1 over R2 plus 1 over R3, where R is the equivalent resistance. When you have two resistors in parallel, let's consider this circuit. The equivalent resistance from our expression becomes R1 becomes 1 over R being equal to 1 over R1 plus 1 over R2, where R is our total resistance. Then when we simplify that equation, we come up with this expression here. We can actually simplify it, because from here what you do, you get the LCM of R1 and R2 is the product of R1 and R2. R2 divided by R1, you get R2. R2 times 1, you get R2. Then plus the LCM divided by R2, you get R1. R1 times 1, you get this, which is equal to 1 over R. Then from here you can easily get the reciprocal. The reciprocal becomes R being equal to R1 plus R2 divided by R1 plus R2. And this equation is what we have here. So when you have two resistors in the circuit, you don't have to go through the derivation. All you have is to quote this formula and then you substitute. When you have two resistors in parallel, the total resistance can be the product of those resistors divided by the sum of those resistances. Let's look at this example. In this example, we are supposed to find the total resistance in the circuit, which has 4 ohm resistors, and these resistors are in parallel, and a battery and a cell which is 1.5 volts. We said that when you have two resistors in parallel, the total resistance R can be calculated from this expression. We said you just get the product divided by the sum. So the first resistor is 4 times 4, and the second resistor is also 4 plus 4. Then what you have is 16 divided by 8. So the total resistance in this circuit is 16 divided by 8 ohms. Let's talk about this example. Still in this example, we are supposed to find the total resistance. We have 3 resistors, the 4 ohm resistor, 12 ohm resistor, and the 3 ohm resistor, plus a battery which is 24 volts. Now our job is to identify which resistors are in series, which resistors are in parallel. Remember, we said that resistors are in series when the current that flows through them is the same. We look at this circuit. Current produced by this battery, let us call it I, at this junction that we are calling junction A, current splits into, let's say this splits to I1 and this becomes I2. I2 is the one that flows through the 12 ohm resistor, and then at this junction, which we are calling junction B, it reunites with the current I1 which flows through the 4 ohm resistor. Then it becomes I again. So you can see that the 4 ohm resistor and the 12 ohm resistor are in parallel, simply because the current that flows through them is different And then here we can conclude that actually the PD across them is the same. If we can call it V1, then the PD across this 3 ohm resistor, let us call it V2. But for a fact we know that 24 volts will be equal to the PD across the 4 ohm resistor and the 12 ohm resistor V1 plus the PD across the 3 ohm resistor V2. Therefore we can conclude happily by saying that the 4 ohm resistor and the 12 ohm resistor are in parallel, but the combination of those two resistors, that is the 4 ohm resistor and the 12 ohm resistor, is now in series with the 3 ohm resistor. Okay, now let us see how we can find the total resistance. Okay, let us start with the parallel connection. Now for the parallel connection, we have the 4 ohm resistor and the 12 ohm resistor being in parallel. So the effective resistance there, or the equivalent resistance Rp, will be the product R1 R2 divided by the sum. And in that case we have 4 times 12 divided by 4 plus 12, and this becomes 48 divided by 16. This gives us 3 ohms. Now if I'm to resketch the new circuit looks like this. We have this 3 ohm resistor, which is the equivalent resistance after the combination, then another 3 ohm resistor, and these two now are in series. Why? It is because the current produced by the current flowing through the circuit, I, will now flow through both of them, and therefore since we are saying they are in series, now the total resistance R will be 3 plus 3, and this gives us 6 ohms, and now that is the total resistance in the circuit. For some questions you can be asked to calculate, for example, the current that flows through, for example, the 4 ohm resistor. In that case they are asking you to calculate for I1, and one can also ask you to calculate the PD across the, for example, the 12 ohm resistor and the 3 ohm resistor. What you have to do there, in Roman number 1 they want us to calculate the current that flows through the 4 ohm resistor here. That means that we know that current from Ohm's law will be equal to V divided by R. We know the resistance, but we don't know the PD. So the first job there is to calculate the PD, or to find the PD across the 4 ohm resistor. But remember, since the 4 ohm resistor and the 12 ohm resistor are in parallel, the PD is the same, and that is V1. But we know that V1 plus V2 is equivalent to 24. Therefore, if I want V1, I can just say 24 minus V2. But the question is, what is V2? Remember, V2 is the PD across the 3 ohm resistor, and from Ohm's law that can be I, the product of I and the 3 ohm resistor. But what is this I? I is the total current. I is the total current flowing through the whole circuit, and it can be calculated from V, which is 24, divided by the effective resistance in the whole circuit, which is 6, then times the 3 ohm resistor. This gives you 24 divided by 6 times 3, that gives you 12 volts. Now if V2 is 12 volts, then automatically V1, which is equal to 24 minus V2, it will be 24 minus 12, which gives you 12 volts. Now that I know the PD across the 4 ohm resistor, I can happily now find the current, and the current becomes V divided by R, which is V, which is 12, divided by the total resistance there, which is 4, and then the current flowing through the 4 ohm resistor becomes 3 amperes. Now, if the current flowing through the 4 ohm resistor is 3 amperes, and the current flowing through the whole circuit I is 24 divided by 6, which is 4 amperes. What is the current I2 flowing through the 12 ohm resistor? Automatically that will be 1 ampere. And it explains that if the resistance is very high, then the current flowing through will always be very low. Because when you compare current that is flowing through the 4 ohm resistor is 3 amperes, and the current that is flowing through the 12 ohm resistor is 1 ampere, it means that current usually flows through a path of least resistance. And so most of the current, which is the 3 ampere, flows through the low resistance, which is the 4 ohm resistor compared to the 12 ohm resistor. In summary, one may wonder, why do I have to calculate the effective resistance or the total resistance, or why don't I just arrange the resistors either in parallel or in series and then I let everything be? Sometimes you might have a circuit, like for example in this circuit, let us assume this 4 ohm resistor here is not there, and then in this circuit you only have the 4 ohm resistor and the 3 ohm resistor. That means that the total resistance in that case will be the total resistance, let me call it RTI. RT prime will be 7 ohms. Therefore the current flowing through the circuit will be V divided by R, which is now 24 divided by 7, and this gives us 24 divided by 7. This gives us 3.43 amperes. But to you realize that this current is actually big or very small. So what you actually do is that you can now shunt another resistor. Bring another resistor. Let us now assume we bring this 4 ohm resistor. Now the total resistance here, first of all you have to first get the effective resistance, because this 4 ohm resistor here and this 4 ohm resistor are in parallel. Therefore RP will be the product over the sum, 4 times 4 divided by 4 plus 4, and this becomes 16 divided by 8, which is 2 ohm. Now this combination here gives us 2 ohms. You realize that now I've reduced the total effective resistance around this area, this region, from here up to here, because this now becomes 2 ohms. Therefore the total resistance, let me call it RT prime, becomes 2 plus 3, which is now 5 ohms. When I do that, now the new current will be 24 divided by 5, and this becomes 4 0.8. So people who deal in appliances, this is what they actually do. If you want to increase the current or reduce the current, you just don't throw away the whole circuit and then come up with another circuit. No, you can either add in another resistor or remove another resistor, because you can see that in this case, the first case, when we had the 4 ohm resistor alone and the 3 ohm resistor, the total resistance was 7. But now when we added another 4 ohm resistor, when we shunted another 4 ohm resistor across the 4 ohm resistor here, the total resistance in the circuit drops to 5. So you can choose to either arrange the resistors either in series or in parallel, depending on the purpose of the circuit. So what actually happens that in series, the total resistance is always bigger than the individual resistances. Like for example, when we have the 2 ohm resistor and the 3 ohm resistor, the total resistance becomes 5. So it is bigger than the 3 ohm resistor and the 2 ohm resistor. However, in parallel, the total resistance is always smaller than the individual resistors. In this case, when we had the 4 ohm resistor and this 4 ohm resistor, the total resistance here in this parallel connection became 2. 2 is less than 4, is also less than this 4. Therefore, arranging resistors in parallel or in series has advantages and disadvantages, like we have discovered. Thank you very much.